adding custom optimization. That I'm not entirely sure what that means, so I will immediately hand that over to you, as I feel like you might be able to explain that.
Yeah, no problem. I will share my R studio. Um, I just made these slides like hours and minutes ago. So if I do have typos or something doesn't look right, just bear with me. And yeah, that's why I also didn't bother to customize anything in Quarto. But yeah, it's all right. Uh, so I want to talk about the optim function and just the basics of it. Um, Optim by its nature um, is just optimization. It's a function that comes with the stats uh, package in R. So it's not something that you have to download. So the stats package, for all those who may not be aware, is the package that does much of the heavy lifting that we do in R. So the stats package will be the home of the AOV function, for example. If you do analysis of variance, which most people do, the stats package is the home of the LM function. If you fit regression models, it's the home of the GLM function. If you do generalized linear models, so yeah, it is the stats package for R, but it also has the optim package, the optim function, which most people don't really use on a day-to-day basis, but it's a pretty neat function. It does a lot of things. So I thought maybe for the sake of those who do not know a lot about Optim, it's better that I make this presentation about it. And we'll just talk about Optim, test it, and see what it can do, because I really think it can supercharge your abilities in taking your modeling into a production environment. For example, if you want to do predictive work, uh, it can do all sorts of things. As an optimizer, it can help you train from the simplest linear models to artificial neural networks, because it's really just an optimizer. But not many people uh, actually realize that some of the big packages in R actually use Optim underneath to find the right parameters for their models. So, like I said in the intro, we want to talk about how it can help us to fit any model to data, as long as we can define an objective function. So, why would we want to use Optim? Um, at a basic level, sometimes we have nonlinear models that we want to fit. Linear regression, generalized linear models, all of them um, depend on us being able to define some linear relationship between our predictor variables and our dependent variable. But sometimes that just doesn't work. Sometimes you have nonlinear models that you know this is how things grow or this is how things behave, but you don't really know how to put that as a formula into your linear regression model in R. So, for example, maybe you know that bacteria starts growing. If you're culturing bacteria somewhere, you know that it starts multiplying really rapidly because it has a lot of food around it in a petri dish, and then it fills up the dish, then it can't multiply as much anymore. Then it's so you have a function that kind of becomes has an asymptote at the end, and then maybe later on the bacteria starts dying. So you know at some point it will go down if it runs out of food, and you want to define a model like that. Maybe you think of a quadratic model, some sort of second order polynomial, but sometimes you actually know how things work. So you know maybe it's a sigmoid function, uh, and other people have published on it. But how do I define a sigmoid function and fit it in R? You can't do that with the uh, uh, linear models unless you transform your nonlinear function somehow to make sense as the normal formulas we use in R. But you can do it with Optim, because Optim will not need you to transform your function in any way. It will not need you to make any assumptions about normal distributions, blah, blah, blah. It will just take whatever formula you have defined and find the right coefficients for that formula. And that's all it does. So I find it to be pretty neat, actually. So, like I said, it it has no assumptions, but we do need to have an objective function. Now, when I say objective function, I mean there must be something that tells us whether we're going in the right direction when Optim is trying to find parameters for us for whatever model we're fitting. And that is the basis of how Optim works. It is the basis of how almost all models work, but R does all of this for us underneath. So most of the times we don't see it. But for every modeling framework we fit, there is an objective function that we are trying to minimize. So for example, when you're doing linear regression, you try to minimize the sum of square errors. And that's why it's called ordinary least squares regression. Basically, when you're doing linear regression, you have your data, you have your X and your Y, and you're trying to find a line that actually minimizes the difference between your Ys and that line. That's basically what linear regression is, isn't it? So the way you do that with linear regression is through some calculus or some matrix algebra. You do that and you find, using this formula here, the right coefficients for the model you have defined that end up defining a line whereby that line minimizes the difference between any data point and where that data point would fall on that line. So this is the objective function, and that's how it works. You can define this. For linear models, obviously, if you use the LM function, underneath this function has been defined for you, and you minimize it and you find your equation and you go away. If you're using Optim, on the other hand, Optim allows you to define this objective function yourself. So it can be anything. So for example, you can do a linear regression, but not minimize sum of squares error, but instead of minimizing that, minimize the root mean square error, or minimize something else that you think is the right thing to target. And that's what Optim allows you to do. You define your own objective function, and then it fits your model to your data based on that objective function. And the way it does that is that it considers all the parameters, well, I can say all the numbers that your coefficients would ever take, and it pictures them as a series of hues and valleys. And the objective of Optim is, for example, if we're trying to minimize the sum of squares error, is to find the set of parameters that, when fitted on your model, result in the minimal sum of squares. So here, where we say the global minima, it tries to find the deepest point in a valley of hues. So it is a search algorithm, essentially. Um, for example, it takes your data and you give it an equation, mx plus c, and you tell it to find the m for you. And it tries, first of all, randomly, just says, okay, first of all, let's say m equals 1. and it tries to fit that line and finds that when it fits a line with m equals 1, the error is 50, and maybe 50 is here on top of the hill. Then it reduces that, maybe tries then m equals 0.5, and it realizes that when it tries m equals 0.5, the error is 60, and 64 is here. It will try again m equals 2, and it finds that the error is somewhere here on the slope. Then it knows that what it must do is increase m. Then it will try a higher m, and it will continue iteratively like that. So it will keep harvesting this hill until it finds this global minimum, which is the right m for your equation to minimize whatever objective function you've set. And that's basically what Optim does. So that works pretty well. For those of you who have done some deep learning, machine learning, you will realize that there are other optimizers that work in similar ways, like the Adam optimizer, the stochastic gradient descent algorithm that people use to fit very complex deep learning models, all use a sort of similar framework where they consider all the numbers that are possible for your data and try to crunch them in and find the numbers that will result in the most minimal error given a data set, and that becomes your model. So we have that in R natively. We don't have to download anything, but it's just that not many people know that it exists, and therefore it's never used. But today we will show you that it can pretty much rival your linear regression, and it can also fit nonlinear models, and that's what we'll do. So let's do that. First, the way I thought I should try it is to just simulate a data set with one dependent variable and two independent variables, and fit a linear regression model on it using the LM function and see the coefficients that LM would give us, and then use Optim on the same data and see what Optim would give us, to see if Optim would give us almost the same coefficients as the linear regression. So first, I simulate the data. This slide just shows some code that I have somewhere here. I'm just simulating some data, and that data is here. It's just three columns, really, a Y, an X, and an X. So we'll use these X's in a linear model to predict Y. And let's see what a regression gives us, and then let's see what Optim gives us. So if we wanted to do a regular linear regression, we would say LM Y equals X1 plus X2. This is something we're all accustomed to, I guess, if you've been working with R for a while. If I do that, and I do my summary, I get this output. And from this output, I get my R squared, but I also get my coefficients, right? So my coefficients are an intercept of 3. X1, the estimate is 2.7. X2, the estimate is negative 1.48. So let's try and fit this same data using Optim and see if we will get the same equation. Because now if we wanted an equation to predict Y, we would say 2.7x1 minus 1.4x2 equals Y, right? So let's see if Optim can give us the same estimates. So to fit this same model with Optim, first we have to define an objective function. So that sum of squares error that regression looks for. Let's define it first. So the first thing I do is make the objective function, and the objective function basically just takes any parameters, and those parameters must be 3, because we're trying to fit an intercept, an x1 and an x2. That's what we're looking for, right? So it says, the objective function says, we take 3 parameters and we will fit the equation that we want to get out of the model. And when we fit that equation, we will see the difference between what the equation gives us, which is a prediction, and the actual y in our data. And please return to us that sum of squares. So it's just an objective function. What you should really think of here is, this is what linear regression does for you underground. It calculates the sum of squares error for every possible parameters and then tries to minimize that. But linear regression does that using calculus or matrix algebra, while optim function will do it by searching across a big feature space. So I've just defined the objective function. And for optim, you have to tell it where to start. So you have to give it some dummy coefficients. So I just gave it zeros. I just said beta 0 is equal to 0, beta 1 is equal to 0, beta 2 equal to 0. And those are the initial parameters. So I'm telling optim, start with this, set everything to 0, find its sum of squares error, and if you're not satisfied, start changing them, start tweaking them until you find the right one. So when I say initial params, I'm just saying this is where you should start. And you can put any number here. You can put 1000, you can put any odd number you want here, and optim will start traversing those hills and valleys until it finds the right one. So the next thing you do now is to use the optim function. So what do we pass to the optim function? We pass it our initial parameters. Then we pass it our objective function, which we set before. We pass it the x1 that we set before. We pass it the x2 that we set before, the simulated data, and we pass it our y. Those are the minimums that it needs. So you're just giving it the data and the objective functions, but you can also choose from a suite of algorithms that it should use. I won't go into them, but there's so many algorithms that it can use to traverse the hills and valleys. And if you pass it that, if you have a particular model that you prefer, a particular algorithm, you can choose. Optim has many of them. So you do that, and it goes and traverses the hills and valleys and brings you back a parameter object. And if you print that out, it tells you that your beta 0 is 3.6, your beta 1 is 2.7, and your beta 2 is negative 1.4. And if you compare them with what we found in our linear model, you will see that they're almost equal. So these are what we found in the regression model, and this is what optim finds. And you can see that there are slight differences, but they are in the third decimal point or something like that. So they're pretty much the same number. But for optim, we have found those numbers without having to assume some distribution, to check to make sure that our residuals are normally distributed. We have fitted this model without any assumption at all. We are just fitting coefficients to data. And we still arrive at coefficients that will rival the linear regression. So that is how optim works. It may sound complicated at first, but it really isn't. And it may sound like, why would I go to optim now when linear regression can do that? Well, for Optim, you can fit nonlinear models. So I want to give a more practical example from my work of how I use Optim to sort of motivate to you why you should consider adding Optim to your tool set, because you will face problems like the ones that I've faced in the past, and you will see that linear regression sometimes can let you down, and Optim can solve the problems for you. Uh, Before I give that example, is there any burning question? Take that as a no. All right, so now let's think about, let's do an example from potatoes. Uh, what you have on your screen is sort of how potatoes grow. This was generated by ChatGPT. I just added the drone and the curve. Um, Potatoes and almost all plants really follow some sort of sigmoid or growth curve. They start out really small and then they grow rapidly until they reach their maximum height that that particular variety can reach. And then they stay there for a while, just absorbing the sun. And as they're absorbing the sun, they're photosynthesizing and they're producing potatoes underground. And at some point, they dry off, and we harvest. Um, this is an important process to understand for those people who grow potatoes, because you are trying to get this potato to reach its maximum height as early as possible so that it can be photosynthesizing at a maximum rate as early as possible. So most potato growers want to know how fast their potato is growing, the day on which it's likely to reach its maximum ground cover, its maximum height, and the day on which it's likely to start drying. Therefore, they can plan their harvest. It's very important, and that's one of the reasons why drones are being used in potatoes a lot, to sort of track how potatoes are growing and then predict how they're going to perform in the future based on that. So when you give somebody potato data, they want to fit some sort of sigmoid growth curve to the data if you give them potato ground cover data. Because from that sigmoid growth curve, they can then calculate how fast the rate of growth, how it changes, the rate of senescence when the crop is drying. But because they have to fit a sigmoid curve here, they will also need to fit another sigmoid curve at the end of the season for when the potatoes are drying. So they have to fit a growth curve and a death curve, essentially. So they have to fit two sigmoid curves to this that go the opposite directions to form some sort of complete growth curve. And that's pretty much how potatoes are modeled. So they end up looking like this. So you have a growth curve going up and then connected to a death curve going down. And most people, this is the bare minimum for potato crop modeling in industry. All growers want to have this curve. And they want you as a statistician, a data scientist, to sort of tell them how fast their potatoes grew, how fast they died, so that they can make decisions for next year. How do you fit that curve? Um, the only curve that could fit here, a quadratic curve wouldn't fit here. It would be too, it wouldn't flatten on top. So what do you do to get a curve that flattens on top like this? You end up having to fit uh, a hyperbolic tangent kind of curve, two hyperbolic tangents connected together, and they look like a double sigmoid curve. And you have to fit that to your data, which you can't even begin to imagine how to do that using your linear regression. But this is what's out there in the industry, and that's what they want you to fit. They want you to tell them how fast their potatoes are growing using that equation. So the way you do that is you take the formula. That's fine. You can define this formula in R. and just use Optim to find all the parameters of the formula. And it's going to do that for you. And that's what we want to try to do. So first of all, you define the formula. This formula here, this function that I've defined is just this formula here. That is the formula that defines this curve. So that's the first thing you do. And that's why I have labeled all the parameters in it, because if you fit this line, A will represent maximum ground cover, B will represent minimum ground cover, P will represent the growth curve. So this equation already gives you everything that the farmer is looking for. So you define it in R. That's the first thing you do. And then you define an objective function. We talked about you have to define an objective function that you want to minimize. And my objective function is really simply the same function that I defined in the previous slide. I use it to make predictions. And then from those predictions, I check the actual ground cover that we got. I subtract the two and calculate the root mean square error. And that's my objective function. So instead of minimizing the sum of squares errors, I'm just minimizing the root mean square error. That's the objective function that I've chosen for now. Once I do that, I read in my data. So I had a ground cover data set somewhere. So this is real data that has been generated by somebody over many plots. And this is how their ground cover developed in their field. And this on the x-axis is the days after emergence, after the emergence of potatoes. And on the y-axis is the ground cover of the potatoes. So you can see the potatoes started really fast developing, and then they reached around 80% ground cover. So they covered 80% of the ground, and then they stopped there for a while. After some days, they started drying off, and they dried off to almost zero and stayed flat like that. So their goal is, can you fit a line here and tell me how fast my potatoes grew, how fast they died, when did they reach ground cover 100%, stuff like that. So I already have my model, the one I want, and I already have the objective function that I'm trying to fit. And all I need to do is give some initial parameters. We said that you have to define some initial parameters. So I define them. These are just really random numbers chosen wisely based on what I know about potatoes. They're just initial parameters on which the algorithm should start optimizing. And once I do that, I check everything to Optim. So I say, Optim, please take my initial parameters and the objective function that I gave you. My observations are the data that I loaded in, and these are algorithm settings that they're just defaults. The good thing about Optim is I can also tell it, whatever you're fitting, don't let it be above 1.6 of the initial parameters I gave you. So don't go wild on this. Don't go looking for a big range of values. And I can also give it a lower minimum. Also, don't go below this, and it will fit that. So when I do that with Optim, I get a final result. And the final optimized parameters can answer all the physiological questions that I set out to collect. And as I've just explained, I wouldn't have been able to fit that with a linear model. I wouldn't even have been able to start. But this fit function that I've just created, this fit object that I've just created from Optim, it has all these parameters that I'm taking out. And these parameters are the optimal parameters of the function that I'm trying to fit. And what I did now is to just use those parameters and fit on the observations and see if I can get a reasonable line. And you can see that the line pretty much fits where it should fit. So Optim has been able to fit a line on my data pretty much exactly where it should be. This is really the optimal centroid of every group of points on every x value. So this is the ground cover, how it developed. And from this curve, Optim has told me that the centroidal maximum ground cover that you would get from this data, considering the noise around it, is around 72% ground cover. And the baseline ground cover where it started is around 0.2. And the growth rate of this crop was about 7% ground cover every day at its maximum growth rate around here. And the senescence rate was higher than the growth rate. Indeed, you can see that the growth rate is much gentler than the senescence. The senescence rate was really fast. So what this is saying is senescence was about 0.23 every day. So the ground cover reduced by this amount every single day when the crop started dying, while when the crop was growing, it was growing rather slowly. And farmers want to know the days to 50% ground cover. So the number of days that it takes for the crop to reach 50% of its eventual maximum ground cover. And it says that was 20 days. And indeed, around 20 days would be somewhere here. The crop's ground cover was around 36% or so, which is 50% of the 72% that the crop actually reached. And it also tells me the number of days to 50% senescence was 90 days. And indeed, at day 90, maybe it's somewhere around here, that's about 50% of the ground cover itself, whatever it reached. And it's telling me this crop likely the most unbiased estimate of the days to maturity for this crop is 90 days. That's what this information means. And through Optim, I can take out all this information and take it back to a farmer and say, given your crop really grows rapidly uh, by day 19, and it grows at about 7% ground cover every day at that point, but it starts finishing on somewhere around day 90 is the right maturity date for your crop, and it decreases its ground cover by about 23% every day. It really decreases rapidly, so it dries really fast. And using this information, the farmer now has a complete understanding of their crop, and they can take decisions going forward. For example, when should I harvest? And they know that after 90 days, their crop usually dries off. Then they can start making real life decisions from it. So all of this wouldn't have been possible with just a plain old linear model or some mixed effects model or some machine learning model. You wouldn't get out all this information. But adding the power of subject matter expertise plus an optimizer like Optim, you are able to get this. So, what should you be aware of when using Optim? First of all, you may have noticed it doesn't give you any uncertainties. So, it doesn't give you confidence bands. It just gives you the optimal set of parameters. So, as a statistician, if you want to report uncertainties, then you have to do some bootstrapping. So you can bootstrap and generate confidence intervals for your data, but also it can run into local minima. So it can be traversing those values that are talked about and get somewhere really deep, but not deep enough, and think that it has reached the optimal parameters. That can happen, but there are ways around that. There is something called a differential evolution optimizer. It's there in R as well, that can help you avoid that problem. But by and large, Optim can solve many complex problems. I've used it in R, I've used it in Python, I've used it to publish papers, I've used it in industry in a production environment where people are predicting at a continental scale, for example, how latitude affects crop maturity, used from satellite data, from drone images. So Optim is it's pretty much everywhere, but it's not talked about much in academia because of this. Because people like p-values, they want to generate uncertainties and confidence intervals, and not many people are confident with bootstrapping. So they sort of shove it aside and pretend it doesn't exist. But this is an algorithm that you will benefit a lot if you add it to your toolbox. And that's what I had. Thank you.
Awesome. Thanks, Joe. Does anybody have any questions? I did have a question in terms of when you got the sort of outputs and you were saying it like senescence decreased by like 20 something percent a day.
Yeah.
Was that like relative 20% or like a continuous 20%?
So it is, let me reshare. It is really just the best nonlinear unbiased prediction of that value.
Yeah.
It is the decrease rate of a sigmoid function at the point of 50% when it's going down. So it is really a point value on this specific point. So the senescence rate, if you just go slightly up, will be different. If you just go slightly down, will be different as well. But you want one value to represent this entire phenomenon of death, right? And the one value, the most unbiased estimate of it is to just get that tangential value right here in the middle. And that's why it's reported as days to 50% senescence. So it is exactly at half of this senescence curve. Um, so it is largely a calculation born out of how the data came out. Yeah.
Okay, cool.
So it's the same for growth as well. The growth rate, there's so many problems without using something like this. And how do I define, for example, for a crop that grew like this? If somebody asks you, how fast did the crop grow? It's different at this stage, it's different at this stage, it's different everywhere. And that's the whole problem of deciding growth rates in functions that are not linear, right? So you have to find the most unbiased estimator of growth. And the most unbiased estimator of growth is the maximum growth rate of the canopy when it was growing. And you will get the maximum growth rate at half of this upward sigmoid curve. And that's the days to 50% ground cover. So on day 20, the growth rate was 0.97. And that is the value that it's sort of an industry accepted unbiased estimator of growth rate. Yeah.
Okay.
All right. Any other question? If anybody is interested in using Optim in their own work, and maybe this is not clear, of course, we'll share the slides and the code. but I've used it long enough to give you one or two pieces of advice. So give me a shout, especially those who have very non-linear problems that they're working on. Yeah.
You'd be able to sort of use it to compare between like different potato varieties and things like that.
Yes, well, that was pretty much my previous job.
Oh,
So
sure.
I used Optim on 30,000 potato lines that a breeder is trying to release, and the breeder is interested in releasing the potato that matures earliest. So you use Optim to fit this curve on 30,000 potato lines and give out this growth rate value.
Mhm.
And they compare different lines and different replicates and do statistical models from it to select the one that has the biggest growth rate and also that reaches this days to 50% ground cover earliest. So they want to minimize this debt and maximize this value. So it is used by breeders a lot to compare varieties and select what grows fast. That's how they release early maturing versus late maturing varieties of potatoes. Yeah.
Mhm. Okay. And do you think you'd be able to use it in terms of if you were applying a treatment to something and you were looking at differences, I guess, across
Yeah.
time?
Yeah. Yeah. I've
Oh.
also used it to not even study ground cover, but study leaf area index when I've applied different levels of nitrogen. Uh,
Mm.
the different levels of nitrogen will cause this curve to produce different shapes. Actually, one of the reasons why this curve is specifically in the way that it is, where is it? This formula is because it is flexible enough that it can be asymmetrical or symmetrical. It can take all sorts of forms according to your data. And if your data is changing according to some treatment, like nitrogen or something like that, it will be flexible enough to pick out the differences in growth rate. So yeah, it works as well with that.
Okay. Cool.
All right.
Awesome.
That's me.
If no one has any questions, we can wrap it up. Thank you to Joe for presenting today. That was super interesting. And I'm also a fan of potatoes, so that was great.
Nice.
Yeah, just a reminder to people that if at any point you feel like volunteering to give a presentation, that is completely welcome. Just drop me an email and let me know. Or if you even just have an idea of something that you want to maybe learn about a bit more or something, and we can look into doing something on that topic. Yeah, just drop me an email. But yeah, awesome. Thanks everyone for coming, and thanks again, Joe, for presenting. And I hope you all have a good evening.
Thank you very much. Bye.
Bye. Thank you.
Bye.